Like a lot of tedious implementation. Okay, so the pulse starts with the seed parameter. Each time the spin is the internal roll number times the pulse. The first roll we start from the first face. For the next roll we start from the previous one. Roll number is initially 1 and is incremented each time the die is rolled. Okay. And then the spin value is added to the pulse modulo by the seed. Increment it, add the roll number, add the seed. This looks convoluted, but okay. Let's see how this. Okay. Okay, so it's gonna have the input of its ID faces and seed. And then we have an initial pulse equal to the seed and an initial roll number equal to it. And so if we want to roll the die, we calculate spin equals the roll number times the pulse. Face initially 0, self.face equals self.face plus spin modulo the number of faces. Add the pulse value to the, or the spin value to the pulse, modulo by the seed, and then add 1 plus the roll number plus the seed, and then increment the roll number and return the face that we're at. Okay. So if we let's try this. Die equals die with ID 1 faces 1, 2, 4 minus 1, 5, 7, 9, and a seed of 3. Get a rolls of -1, 9, -1, -1, 5, 4, 4, 2, 5, 2. Okay, great. Simulate consecutive rolls of all the dice simultaneously and add the number of rolled digits as your points. So as an example here, okay, I get it now. So let's see. For each line, we have 3 items separated by spaces. So parts equals line split, ID equals parts 0, and then we cut off colon and turn it into an integer. Faces equals this part with these 7 characters cut off, or rather 8, because then we also want to cut off brackets, and then we split that by the comma and turn each part into an integer. And then the seed is equal to, we cut off these 5 characters. So this will hopefully work. Perfect. Okay, so now we just need to have a list of dice, and then just do dice dot append a new die like so, and then we just need to keep rolling. So rolls equals 0 while true, rolls plus equals 1. We also need a total. Total plus equals the sum of each die's roll. And then if the total is greater than or equal to 10,000, we break and then print out the total number of rolls. What? Oh, come on. Instead of valleys, it gives faces. Why does this part have a different input format than the rest of it, than the test cases? That's actually annoying as hell. 6, 4, 8. Cool. Okay. I guess I shouldn't be using slice like this. I should do dot split on the equal sign and then grab the first part and then cut off the brackets. And same for this one. Yeah, so this one should now work regardless of the input format discrepancy. Okay. Let's see where we're at here. The racetrack is a sequence of random numbers from 1 to 9, matching the possible outcomes. If the number rolled matches the number of a space they're currently on, they can move forward. Okay. All players roll their die once per turn, and each of them starts on their respective spot. Okay. Oh, I see. I see how this works. Okay. So, um, going with this as our example, we'll break when we get a space and then, or no, that won't work. Or so I should be doing this in the part 2 file. Okay. Um, cool. So, and then the track will be like so. So we should have a list of right, wrong. Okay, so we have a list of dice and a track, which is a list of numbers. Cool. So now, basically for each dice, we need to track how many turns it takes. So turns equals 4 die in dice. We'll keep rolling until we get through the track. So 4 next in, or 4 X in track. We'll keep rolling until we get that. So turn starts at 0. For every time we start up a loop where we roll the die and see if it's equal to X. If it is, then we break out of this while loop. Basically, what we're doing here is for each die, we want to determine how many rolls it takes to get out of the track. So we go through each space in the track and keep rolling until we roll the correct value. And then we do turns, they'll append turn. And so this should give us the completion time. So here that's at 61, 80, 65, 79. And now we just need to sort the dice by the turns. So what we can do for this is indexes equals, basically what we're trying to do is we're trying to determine the order of these. We're not trying to sort the list, we're trying to sort the indexes by the list. This is easier in other languages, but in Python, I think what we can just do is do something like this. And then if we sort with the key equal to given an index, return the number of turns that index took, then we'll have those in the right order, and then we just need to add 1 to each of them because the problem wants the 1 indexed. It's a long track. And hopefully this will be correct. Perfect. Finally, for part 3, the game is played on a grid of squares. Okay. Fancy. Each from 1 to 9 at the start. Every space has a coin. Players place their tokens anywhere they choose and roll their die. If the number rolled does not match, then the player dies. If it matches, they take that coin, and then they can move 1 in any direction. Oh dear. Oh dear. The fact that they made map art using this is actually really cool. I want to know how they did this. Okay. What is the maximum number of coins that can be won by the last survivor in this game? How does this work? So the number of each play. Okay, each player can start at a grid. Oh, I think I understand how to do this. We start with a die, we roll it, see where it can start, and then we keep repeatedly rolling and filling out all of our possible paths, and then see how much the grid is occupied. Okay. So for this, let's start with a smaller, a bit more approachable of an example. Okay. So this time instead of a track, we'll have a grid. And then we'll do grid equals list map into row for row in grid. Split by new line. Okay. And so for each die, we'll want to fill out the grid. So um, we'll keep track of which coins can be collected using a set of coordinates. So let's call it possible. And then we'll want to go through each die and fill out all of the possible survivors that could have all of the possible spaces that can be reached from there. So we'll start with or die and dice again. We'll start by selecting all of the possible spaces that a survivor could start in, such that when they roll this die, they don't immediately lose. So we'll first roll the die, value equals die.roll, and then we'll select all possible coordinates for them to start at. So we'll call this set the open set, as in it's, or I guess not open set. Let's call this one possible and this one aggregate. The possible set will start out as the set of all coordinates for row in range of the length of the grid, for column in range of the length of the row, if that coordinate is the value. So in this example, we can see that since our first roll is 5, we can only start at the coordinate 0, 1, which is here, row 0, column 1, 0, 5, which is here, or 1, 7, which is here. So these are the only 3 spots that we can start. All other spots are immediately eliminated. And so we'll add all of these possible spaces to the total aggregate, and then we'll just keep going from there. So basically, for while the possible set is not empty, we'll get the next value, and then we'll look for all neighbors of a current possible spot that we could have gone. Basically, we're retroactively figuring out where we move. We're first seeing where we could start after we determine what the roll will be, and then we'll see what the next roll will be and see where all of the possible positions we could move to that allow us to not lose here is. So I don't think there's any exclusion about backtrack, right? They can also stay where they are. Okay, so there's no mention that you can't walk back to a space without a coin. So in that case, we'll look for all possible neighbors. So next set will start out as the same set as possible because you could sit there. Or no, we'll start out empty. And then for each possible coordinate, we can move in any direction by 1 square or stay in the current spot. So for next row, next column, or neighboring row, neighboring column in set of possible moves, we'll first check if the row or the column is less than 0 or is out of bounds. and we can immediately skip it. If that space is not equal to the next roll, we can immediately skip it, and otherwise we'll add it to our next set of possible moves. This should say NR. Actually, this should all say NR, and this should say NC. What we're doing here is we're basically figuring out what all of the possible spaces we could have moved to from our previous possible positions is such that we don't lose the next roll. Then we'll do next set or possible equals next set, and then aggregate. What we're doing here is so long as we have possible spaces we can move to, we'll roll the next die, or get the next roll of the die, see where all of the possible spaces we could be are, set that to the possible positions, aggregate all of those positions, and then repeat. At the end, we should just want to get the number of aggregate values. So we see here that the maximum is 33. This should give us a value of 1125. And this grid will probably take a bit to run. Give us 156712. Cool. Okay. Given that this example has like a money bag as the artwork, I do highly suspect that my input will also have some artwork, so I do want to see what it might look like. Oh dear, this is a large grid. Okay. I think the way we're going to do this is for R in range length grid, for C in range, or no. I'll make an art grid of just a bunch of spaces. Like so. And then if we print each row of the art like so. All right, let's not use the big example. Let's use the small example first. That'll give us that, and then we can say for RC in aggregate, our RC equals £, and then we can output that to output.txt. And now if we try that on the bigger grid, there we go. We get our artwork. And now if we try that on a really big grid, this might take a second. We get, now that's cool. Now that's really neat. Thanks, Emil. Thanks for the challenge. Today's was really fun. Yeah, I got there faster than I thought I would, but this artwork is really cool. It would be a fun challenge to figure out how exactly to construct artwork using this challenge. I think I guess you can make a bunch of completely random dice and then every square you want to draw and you just set a number that you can start at and then use halves of those numbers to draw out the it's a cool idea. I think I have some ideas how I could do it, but definitely really neat. Yeah, this was fun to do, and I'm glad you had fun preparing it too. Pretty awesome challenge today, especially with the effort put behind having artwork. I hadn't even thought about that possibility until I saw that you had the cash bag thing in the second example. So I figured I'd print this out, and it certainly did not disappoint. Cool. All right, I guess it wouldn't hurt to go back through the earlier parts a bit because I did breeze through that pretty quickly. See if anyone else is on the leaderboard today. Hmm. Uh, Find a higher. Oh, right, because salt. Okay. Well, best of luck to Jonathan. Um, but yeah, we were worried people wouldn't notice. Yeah, I'm glad you put that there because I hadn't thought about that. Because I was figuring I figured it was mostly just the number that you cared about. But since you drew out the paths for, yeah, I'm glad you put that there. Um, yeah. So the reason I decided to approach this using a die class is because I figured that it would be the easiest way to track the state. You could also track each die as just a tuple of values and then have like a transformer function. So basically, you could store all of these values in a list and then have a function to take the current die configuration and output the next die configuration as well as the roll. But that seemed a bit more complicated than just having the die track itself. And I figured it would probably be all right and we wouldn't have to like search through. Well, given that the die is just a generator for a sequence of numbers, I figured it was fine. Um, could have honestly made it a generator too, like an actual Python generator, so that you could just iterate through the die. But this seemed a bit more straightforward to approach, and I'm not that experienced with generators. Could probably wouldn't be too hard. I guess you could just do like def die ID face. The ID is actually not needed. Faces seed. You start with the pulse equal to the seed. Roll number equals 1, face equals 0, and then I guess you just do while true spin is self dot roll number or not even self. Spin is roll number times pulse. Face is face plus spin mod the number of faces. Pulse equals pulse plus spin mod seed plus 1 plus roll number plus seed roll number plus equals 1, and then yield self dot faces face. Now, theoretically, that should work if you do like 4x in a given die of like, let's go back to the first example. 1, 2, 4, minus 1, 5, 7, 9, and 3, print x. Um, did I do that in the, why did I do that in the part 1 file? Okay. Yeah, that would have worked perfectly fine as well. Oh dear, that generated a lot of lines fast. Yeah, this would have worked too, but I came up with this approach first, and it seemed relatively straightforward. Either makes sense in my opinion. Um, I'll leave this here commented for anyone who might want to look through the code afterwards. Okay. And then the first part was fairly straightforward. We just need to parse the dice and then keep repeatedly rolling until we hit a total of 10,000. Not gonna bother. For the second part, yeah, basically we just want to see for each of these dice, how many rolls does it take to get through these numbers in sequence. So we just repeatedly, for each die, we check how many rolls it takes, wherein we start from... We basically go through each item in the track and then keep re-rolling until we roll the correct value so we can move to the next square. also fairly straightforward. And for the last one, it was more or less just a flood fill. There was no. This is reminiscent of breadth first search, but it's not really a search algorithm. We basically just repeatedly roll a die and see what the possible values are. Roll a die, see where the possible values we could end up in are, and then just repeat that until we get the value. Yeah, I guess for the purposes of uploading this code to GitHub, I'll have it print the length of the aggregate and then write the arc to a file. So I guess with open output dot no, that's what is the makes sense to print a standard error in that case. File equals standard error. And so that way if we do part 3 like so, we'll get the number and we can get the artwork, and then I can just pipe the artwork to output.txt and keep the value in the terminal. Cool. Very fun challenge and very fun story overall. I'm looking forward to doing the full what's it called, event in November. I'll stick around if anyone has any questions, but other than that, thank you for watching this mini 3-day series, and I don't know when I'll next stream or make a video, so it's very possible that I'll see y'all in November. Hopefully sooner, but we don't know. I'll stick around if anyone has any questions or wants to mention anything that I might have missed or that they want to bring up.